problem is this: we have a probability measure on Rn that drifts along the vector field. Can I use it like a... Yeah. It drifts along a vector field that depends on some control parameter, and we want to control this process. Actually, the evolution of theta can be described in this case by the following continuity equation. So this mass transportation problem is a control problem for the continuity equation. So first of all, I'd like to depict this. What does it mean? And thank you. So here is the definition. So if you have a time-dependent vector field, then the big solution is defined as usual. So it is a curve in the space of measures, and for every test function, this curve must satisfy to some some integral equation. So the usual definition of big solutions. Okay. What was the motivation? Actually, what is really interesting is to control local continuity equations. When you have a measure also in the vector field, these equations have a lot of nice applications in traffic modeling, crowd dynamics, and so on. But before studying control problems for this, it's hard equations, it is reasonable to ask what is known for the usual continuity equation. And surprisingly, it appeared that not so much is known. Since I will talk about controllability, I can say only about this paper, Roger and Rocket, where this question was touched upon, but only in the case of linear vector fields, and I don't know actually any other papers. So, okay. To deal with the continuity equation, we need two very simple notions. They are well known actually. First, the flow of a time-dependent vector field, so it's easy, and I don't want to talk about it much. And so first notion is a flow, and the next notion is a notion of push-forward measure. So when you have two topological spaces and a continuous map between them, and you have measure on x, then you can get a measure on y by this simple formula. So this second measure is a push forward of the first one. But probably it's better to think about push forwards in the following way. So you have a continuous map between two spaces, and you have some sharp operator. You apply this sharp operator to f, and you get a continuous map between spaces of measures. So it's easier. And yes, this map is continuous if the spaces of measures are linked with narrow topology. So next. Yeah, so let's apply this sharp operator to the flow. In this way, it is easy to see that we get a flow on the space of measures. So a flow in the sense that all these properties are satisfied. And moreover, next slide, this flow actually defines the solution of our continuity equation. So if you have sufficiently irregular vector field, then there exists a unique solution of this Cauchy problem, and this solution is defined by the flow. So you just push forward your initial measure by the flow of the vector field well, what is the implication? The implication is that you can essentially forget about continuity equation. You can talk only about flows and push forwards. So, and actually in the future I'm going to forget about continuity equations. Okay, next. So now controllability. The definition. This is the definition of approximate controllability, and we shall see that here it is reasonable to talk only about approximate controllability. So you have two probability measures, and you want to steer one measure to a neighborhood of another measure. So the neighborhood are in Wasserstein distance, Cantor-Rubinstein distance, and so here it is. So you want to find a control such that the corresponding flow will push theta to a neighborhood of mu. The control is feedback. Well, it is natural because actually this is a partial differential equation. So it is distributed equation and the controls must be distributed. It's an interesting problem when we can do this only for open controls. Okay, so that's usual definition. I think we heard it many times today, but again we have a family of smooth vector fields on Rn, and we take the smallest Lie algebra that contains this family, and we say that. So we evaluate all these vector fields at x, and if we get Rn, then we say that this family is Brecken generated. And the result is the following. So denoted by P C of Rn, the collection of all non-atomic compactly supported probability measures on Rn. And suppose that our vector field is linear with respect to u. Then, and if this family is bracket generating and n is not equal to 4, then this continuity equation is approximately controllable on P, C, Rn. There are several questions. So, yeah, for example, why we consider only non-atomic probability measures? Why we talk only about approximate controllability, and why n is not 4? And yeah, we can see here the answers to first two questions. First of all, continuity equation cannot split delta function into two parts. So if you have an atom, then you cannot get rid of it. So it's make no sense to talk about controllability measures for measures that have atoms. And the second picture, continuity equation cannot steer this measure to this measure. So this one is supported on a segment, and this one is supported on a square. So it is impossible to steer this to this, but we can approximate in the topology of such time distance. The third question, actually, well, I will talk about it later. So the sketch of the proof. The proof is very simple, but it is simple because it relies on three very deep and difficult theorems, and I want to show these theorems, but only for case of Rm. But I must say that they have so that they can be formulated for any smooth manifold. Okay, first theorem is von Neumann, Oxtoby, and Duan. So by names you can guess that it is a very old result, and it was very hard to find actually. So first definition. So you have an n-dimensional cube and you have a probability measure on this cube. We say that this measure is the Lebesgue-like if it is monatomic, if the measure of the boundary is 0, and if any non-empty open subset of Q has a positive measure. So next, actually the theorem. So any Lebesgue-like measure can be steered to Lebesgue measure by a homeomorphism. So here is it. Lambda is the Lebesgue measure, and of course it must be scaled because we deal with probability measures. So you have any Lebesgue-like measure, you can find the homeomorphism that steer it to the Lebesgue measure. And what is important, this homeomorphism is an identity on the boundary. Again, it was really hard to find. I know only one book in measure theory, and this theorem was as an, I think, an example or something like that. But not now when you have this theorem, everything is more or less evident. So, yeah, next. So, first of all, you take any measure, any completely supported monatomic measure, and you must show that it can be approximated by a Lebesgue-like measure. And what is important, it must be approximated in the strong topology, the total variation topology. When you show this, then immediately from the previous theorem, you get that, so given two measures, you can, there exists a homeomorphism that steer one measure to another measure, and this homeomorphism is compactly supported. Next. So, about support, let me recall the definition. So this is supported by homeomorphism. So you exclude all fixed points and make the closure. And two important facts for homeomorphisms in Rn. So any compactly supported homeomorphism is a topic to the identity. And any compactly supported diffeomorphism of Rn is orientation preserving and therefore is also smoothly the topic to the identity. And actually this is why, because everything is simple when you are in Rn. Because next two theorems, this property of isotopic to the identity is the central property. And in Rn it is very, very easy to check. So you just check that your diffeomorphism or homeomorphism is compactly supported. So next result, of course you must approximate your homeomorphism with a diffeomorphism. And you can do this. Actually, much general result is here for smooth n-dimensional manifolds, and here is so n is not equal to 4. As far as I know, nobody knows what happens in the four-dimensional case. It is a well-known special case, and we have different structures, and so maybe it's true, maybe it's not true. I don't know. So we must exclude it. Okay, when we approximate.
I think it is not true.
It's not true.
It is not true. Exactly because we have a lot of smooth structures. Non-standard smooth structures, so they are homeomorphic but not diffeomorphic.
Yes. yes, it seems that it can be true, but I'm not feel much confident
The
in
old
this
homomorph,
area.
if you take homomorphism which transport one into another, I think you should derive from that, but it's not possible.
Maybe. So, okay. So what you have? What you have here, you can steer one probability measure to a neighborhood of another probability measure with a diffeomorphism. And this diffeomorphism is compactly supported. And finally, we should use the theorem of Andrea Grachov and Michael Caponigro about controllability on the group of diffeomorphisms. So if you have a bracket generating family and you have a compactly supported diffeomorphism on Rn, then you can find some feedback controls such that your diffeomorphism will be exactly the flow of this system. So basically, you can talk about controllability on group of diffeomorphisms, or you can talk about controllability in the space of measures. It appears that it is more or less the same. And concluding remarks. So if you have a bracket generating family of vector fields on Rn, you can steer one point to another point using open loop controls, and you can steer one measure close to another measure using feedback controls. And finally, it seems that everything works also on at least smooth, compact, connected Riemannian manifolds. But so here is the problem. So you should always check that all the diffeomorphisms and homeomorphisms in consideration are isotopic to the identity. And so you, it is really not easy. For example, you can deduce from Neumann-Oxford-Ulan theorem that any measure, say any non-atomic measure with support, whose support is equal to your manifold, so to support it on the whole manifold, so you can steer it to another measure by homeomorphism. But who says that this homeomorphism is isotopic to the identity? So you should actually, more or less, you should reprove this theorem, and this is a problem. Of course, four-dimensional case is somewhat disappointing, but maybe there are ways to avoid this. Use some different technique to prove that this thing, but it's really strange if it doesn't work in the four-dimensional case. So, thank you very much for your attention.
Other questions?
My question is not mathematician. Did you see the barrel of Nobel laureate Kantorovich near the entrance to the institute? This
No.
institute.
But
Okay.
maybe I saw it.
I saw.
I know that in Novosibirsk I should say Kantorovich with Einstein distance instead of Wasserstein distance.